Okay, in this video we're going to be describing work and energy. All right. The unit for work is joules. The reason why is it takes a lot of work to give a girl a joule if you want to. It took me a long time to give that diamond ring to my now wife. Hope she doesn't find that offensive. Okay, work and energy. For our discussion in this video, we're going to limit it to examples of forces in the direction of the motion or opposite the direction. So here I have a green block, and let's say I apply a force to it to the right. There's also going to be a force of friction that's between the wall of the block and the actual ground, right? So that's going to be an opposing force due to friction. When we're actually looking at our work, the work applied will be based on the positive direction to the right, and it's the force times the displacement. That's where the block started to where the block ends. Okay, here we're going to have a student describe the equation for work.
The work done by the force is W equals F times D, where the F equals force and D equals displacement.
So all you do to find the work is you multiply the force times the displacement, and remember the displacement is where the object starts to where the object ends. Like I said in the beginning of the video, the unit for work is joules. That comes from the scientists that discovered the equations and laws for work. It's also the unit for energy, and it's also the unit for heat. If you look at heat, calories and joules are two units you use. Like calories is the unit you use for food when you're eating it. It's also the amount of heat that gets released. 1 calorie is about 4.18 joules. Okay, we're going to have a student describe the next slide.
Work and energy. Energy, one definition for energy is the ability to do work. There are two main categories. Kinetic, the energy of an object in motion, and potential, the energy of position.
Good. So kinetic energy is when an object is actually moving. Potential is the energy due to the height of an object. So if I look at this rock over here, right now it doesn't actually do any work because it's just resting on top. But if I release that block and it starts falling down, let's say my foot was down in the ground, it's going to hurt my foot. So it had the ability to do work, right? And the kinetic energy will be equal to the potential. If I left the block higher up, it's going to have more potential energy, and that means it's also going to go faster on the ground and have more kinetic energy. So let's look at potential energy. You have different subcategories, because remember it's the ability to do work. You can have gravitational, that has to do with the height of the object. You can have elastic. Elastic has to do with, say, a rubber band or a spring. Think about a pinball machine. When you pull back the spring and you didn't let go yet, it still has the ability to hit the ball. And you also have chemical energy, right? You might have a chemical reaction occur and that releases energy as well. So again, energy is in two types. Kinetic energy, which is motion, and potential energy. Kinetic energy, the equation, you can find these on your reference materials that you can use on your tests. Kinetic energy is equal to 1/2 times the mass of the object times the speed squared. So, if an object goes faster, you're going to square that speed. It's going to be a lot more energy that way. Potential energy is equal to the mass. Think about a boulder compared to, say, a ping pong ball. The boulder will hurt my foot more if it falls on me. Times gravity, we're going to use 9.8 for gravity on Earth, times the height. If I drop the same ball from increasing heights, so let's say I have a ball right here and then a ball lower, the ball that's higher up is going to have more potential energy. Elastic potential energy is 1/2 times the spring constant times the displacement squared. You notice that they're very closely related to the kinetic energy equations. All right, I'm going to have a student describe the next slide.
Law of conservation of energy. Energy cannot be created or destroyed. It can be changed from another.
Good. So another way to think about this equation is the amount of work that I perform is equal to the amount of energy produced. Work and energy are like two sides of the same coin. One could be changed into another. So the example of that one is, let's say I take a block and I push it up a little ramp. When the block goes up the ramp, now the block has potential energy, right? Because it's at a certain height. Another way to write this equation is work equal to energy, or Ewok. Think about the Ewoks in Star Wars. They're able to stop the stormtroopers from getting in the forest. Work and energy, again, two sides of the same coin. And your unit for both is joules. You can use capital J for that. Okay, let's look at a situation where we have a boulder. It's 10 meters high, and it's a 5 kilogram boulder. Let's say the question asks us, how fast will the boulder or the velocity hit the ground? When you're doing questions like this, you want to think about what's happening in the beginning of the situation and the end of the situation. In the beginning, I have potential energy because the block is at a certain height. At the end, I have kinetic energy because the object, the boulder, is moving and there is no height at the ground. Next step you want to do is write your equations. For PE, it's mass times gravity times height. Like kinetic energy equals 1/2 mv squared. And those you can look up. You don't have to memorize. They're in your formula chart. When I want to solve this, you notice the mass is on the left, the mass on the right. They could cancel out because any number times itself will be the same thing. Next I have G is 9.8. The height of the wall is 10, equal to 1/2. I don't know my speeds, that's what I'm trying to find. I'm just going to write v squared again. Next I can multiply 9.8 times 10. I get 98 on the left, equal to 1/2 v squared. To get rid of the 1/2, I could divide by 1/2. So if I divide by 1/2 on this side, you got to divide by 1/2 on that side. The 1/2's cancel out. I'm left with 196 equals v squared. Last step, I got to get rid of the squared. The opposite of squaring something is to take the square root. If I do square root on one side, square root on the other. Square root of 196 is, let me use my calculator, 14. My unit, since I have kilograms and meters, will be meters per second. So again, when doing these, you want to write the situation, draw a picture of it, write your equations next, right below it, write down the variables in the equation, and then use math to solve for it. Alright class, so that's a good overview of potential and kinetic energy. If you have any questions, please leave a comment down below or shoot me an email at kaminskil@hayescisd.net. Use the potential that you have.